Okay, so let's get started. Hello and welcome everyone to week 11 of interactive live sessions for the course on fundamentals of convective heat transfer. This course is being offered by NPTEL. It's being instructed by Professor Amaresh Dalal from the Department of Mechanical Engineering at IIT Guwahati. My name is Debjit and I'm a PhD scholar at IIT Madras and the TA for this course. Now, like every other week, we shall be solving some problems together. Let's head into them. So, first up, we have question number one, which is asking us that the condition for moderately intense turbulent flow. So, these words are important here. Moderately intense turbulent flow field is given by where I is our parameter here. I is the relative magnitude of the root mean square value of the fluctuating components with respect to the time averaged mean velocity. So basically that's how turbulence intensity is defined. It's the root mean square of all the fluctuating components. So it will be u prime square plus v prime square plus w prime squared, and this will be normalized with the uh, time averaged mean velocity. So if it'll be u bar plus v bar plus w bar, or rather the root mean of that as well. Right. Or not. Let me write this correctly. Uh, this, yeah. So this is how we define the turbulence intensity I. Now there are some options given here. The options A, B, C, and D, which are different ranges of values of I. So option A says I is less than 1. Option B says that I is between 1 and 5. Option C says that I is between 5 and 20. And option D says I is greater than 20. So which of these corresponds to moderately intense turbulent flow? Let's look at the answer. It's actually option B. So going through all of them one by one. So I less than 1 is basically low turbulence. It has just transitioned from laminar to turbulent, and the intensity of turbulence is not as much. When it's between 1 and 5, we have significant amount of turbulence, and we call that moderately high, moderately intense turbulence. If it goes higher, we call this high turbulence, and greater than 20, it's extremely high turbulence. So these are just conventions. These are not numbers set in stone, but it gives you an idea about how significant is the turbulence in a given problem. Okay, so the simple one. Moving on, we now move on to a more important question, which involves the scaling given by Kolmogorov. So the question is asking us to consider a steady, fully developed turbulent flow of water in a horizontal pipe if the Kolmogorov length scale is given by 0.87 microns. What is the mean dissipation rate in kilowatts per kilogram? So given that you can take the viscosity of water as so, as 9 power 10 to the power minus 7, 9 into 10 power minus 7 meter square per second, and the relationship between Kolmogorov length scale, the viscosity, and the dissipation rate, epsilon, is given. So, yeah, so given this information, you have to find what is epsilon and in kilowatts per kg. So if we take a look at the solution, it's option B, 1272. Let's see how we can get there. So the process is pretty simple. So the length scale we know is equal to nu power 3 by epsilon power 1 by 4 as given in the problem. So we multiply, sorry, we take a power of 4 both sides. So we have LD power 4 equal to nu cube divided by epsilon. We need epsilon. So epsilon would be nu cube by LD power 4. Now we just substitute the values. So it's 9 into 10 power minus 7 powers 3 divided by the length scale which is given. So that is 0.87 into, this is microns. So 10 power minus 6 power 4. Let me quickly do this calculation. So we have 9 multiplied by 10 power minus 7 power 3, and this has to be uh, it has to be now divided by 0.87 into 10 power minus 6 power 4. Yeah. So what I get is around, oh, sorry. So what I get is around 1272 uh, 478 point something. Let's say 69. This much watt. Now the watt per kg. Now given we have to find in kilowatt per kg, we'll just simply divide by 10 power 3 and we will get something like this. 48 kilowatts per kg. Now rounding off, we get 1272, which is option B. So that's how we can easily arrive at the solution. Now moving on to the next question, question number 3. Now this is asking us that two statements are given. You have to pick which statements are correct, and then there are some combinations of correct and incorrect statements in the options given below. You have to pick out the correct combination from there. So the two statements are statement one is the most important mechanism for generating and maintaining turbulence is shear in the mean flow. And option two says, and these are all important keywords, shear in the mean flow. And option two says turbulence dies out due to viscous damping unless some mechanisms keep on pumping energy into the velocity fluctuations. So these are two statements. You have to pick which ones are correct. The given options are option A, only statement one is correct. Option B is that only statement two is correct. Option C is both statements one and two are correct. And option D is none of the statements are correct. So what do you think? Which option should it be? Which ones are correct? Let's take a look at the solution. It's actually option C. Both statements are correct. So we look at them one by one. The first one, the most important mechanism for generating and maintaining turbulence is shear in the mean flow. So if there is no shear, then what I mean by shear is a gradient in the velocity. So let's say I have a velocity profile which looks something like this. So unless I have a shear, if I have only a uniform flow field, that doesn't have motivation enough to shift to turbulence. The main reason is that these velocity gradients, they become unstable at certain Reynolds numbers. And that instability then those instabilities grow, the disturbances or minimal perturbations which you impose on the flow field, and these are naturally present in most cases, in all cases, all natural cases. So that causes these perturbations to grow, and that's what leads to generating as well as maintaining turbulence. So it's the shear that is a necessary condition for creating turbulence. So this is a necessary condition, not a sufficient one, but this is important. And the second statement tells us that turbulence dies out due to viscous damping unless some mechanisms keep on pumping energy into the velocity fluctuations. So that is true as well. So let's say I have something like a flow or a flat plate, and this boundary layer becomes turbulent at some location. So it could be due to, surface roughness or things like that. So if I just create one perturbation, and that perturbation will ultimately die out due to viscous damping. That's what happens in energy cascade as well, that there are big vortices forming and they keep on breaking up into smaller vortices, which ultimately disappear. So only one singular event of creating some fluctuation won't really sustain. They will die out due to viscous damping. But for sustained turbulence, you need mechanisms which keeps on pumping energy. So let's say this surface roughness, for example, as long there is a flow coming in, this will keep creating these vortices, which will go downstream and probably decay into smaller eddies and so on. But here, this generation of newer fluctuations keeps on going, and that's necessary for sustaining turbulence. So that's why statement 2 is also correct, and the correct combination which you should have chosen is statement C, that both statements 1 and 2 are correct. All right, so let's move on. We'll move on to question number 4. This is a conceptual question. You have to think a little bit. So it's asking us that what can turbulence cause in internal flow? Is it option A, decreased pressure drop, decreased heat transfer? So I'll just write them here. So pressure drop is P. I have, internal flow, something like flow in a pipe. So there's delta P and there's heat transfer. So that's a Q. Q dot. This is total heat transfer, not just per unit surface area. Anyway, and this is also total pressure drop, not just pressure gradient. So in an internal flow, what can turbulence cause? Now you have to, so this increased, decreased, these are in relation to something, and that relation is, you can think in relation to laminar flow. So in case you have a flow situation in which you switch from laminar to turbulent, then what happens? Does it lead to a decreased pressure drop and decreased heat transfer according to statement A? Or option B says increased pressure drop and increased heat transfer. Option C says increased heat transfer but decreased pressure drop. And option D says increased pressure drop and decreased heat transfer. So there are four options. I'll write them down here. So option A says both of them decrease. So this decreases, this also decreases. Option B says both increases. So this increases, this also increases. Option C says increased heat transfer but decreased pressure drop. And option D says increased pressure drop but decreased heat transfer. Which one do you think will be caused due to turbulence? So let's take a look at the solution. It's option B. So if we go back, so pressure drop increases due to turbulence, right? That's because uh, the shear uh, stress on the wall increases. So in case if you have a laminar flow, you have a parabolic profile like this, and let me use a different color. Sorry. And in case if you have turbulent flow, you have a more flatter profile in the center and a more sharp uh, velocity gradients near the wall. So that leads to a higher shear stress, which has to be overcome by this pressure difference. So this pressure difference increases. Now, what happens to the heat transfer? There is increase in this gradients of temperature as well, and that increases the heat transfer rate as well. So let's say if I now draw the temperature gradient, we know that this is kind of what laminar flow temperature gradients are. So let me just stick to the same color. So in a turbulent case, I'll get something like this. And in a laminar case, I would have gotten something like this. A more smooth gradients near the walls. So since these gradients become sharper, the heat transfer rates will also increase. So heat transfer would also increase. So the correct combination would have been increase in both, and that is seen at option B, increased pressure drop and increased heat transfer. And these are important properties which become relevant in case of industrial applications, where let's say in an heat exchanger you want to increase the rate of heat transfer. So you decide to trip the flow and make it turbulent. So there turbulence gives you the advantage of increased heat transfer. But that comes at a cost as well, which is increased pressure drop. So now you have to increase your pumping power as well to maintain that turbulence. So that's disadvantageous in this case. So your cost would increase. But then again, these trade-offs exist in engineering so that you can, understand them and make an educated decision on what to do, what would be the optimal thing to do. All right. So moving on, we'll move on to question number 5 about the phenomenon known as energy cascade. This is very important in turbulence. So the question is, which of the following statements are true for energy cascade? So option A or statement A is that the smaller eddies combine to form larger eddies and larger eddies combine to form further larger eddies and so on. Option B says the small eddies remain contributing to the disturbance growth. And statement C says that the large eddies break into smaller eddies break into still smaller eddies, and so on. And option D says all of the above. Which one do you think is correct with respect to energy cascade? Let's look at the solution. It's actually option C. The large eddies break into smaller eddies, and smaller eddies break down into still smaller eddies, and so on. So as you can see in this figure, this is the direction in which this is the phenomenology of turbulence. So bigger eddies break up into smaller ones, and they keep breaking up into, subsequently smaller and smaller. And the smallest eddy which can form is, that's of the length known as the Kolmogorov length scale. And beyond this, they just, dissipate away into heat. So you can imagine that there's a very small eddy, and that has very small energy to begin with. And whatever energy it has, it gets dissipated as heat because of viscosity. So this is the natural phenomenology of turbulence. Now, the first option, that smaller eddies combining to small form larger eddies and so on. So it's not that this never happens. Sometimes this happens, but it's a rare phenomena, and this is known as the inverse energy cascade. But option B is not right at all because smaller eddies remain contributing to the disturbance growth is not true. So all fluids have some viscosity and that will lead to the smallest viscosities to lose out their energy. They don't have infinite energy to remain contributing to the disturbance growth. They will contribute and dissipate away as well. So it's option C that should be the correct one. All right. So moving on, we'll move on to question number 6, which is asking us that according to Prandtl's mixing length theory, which is a very important concept, what is the turbulent eddy viscosity eta T given by? So there are some mathematical forms here. You have to pick the correct one. So option A is nu T equal to kappa y square into the modulus of dou u bar dou y. Option B says it's nu T equal to kappa y into the modulus of dou u bar dou y. Option C says it's nu T equal to kappa square y square into modulus of dou square u bar dou y square. Or is it option D, eta T equal to kappa square y square dou u bar dou y? Which one do you think is the correct expression for turbulent eddy viscosity given by Prandtl's mixing length theory? Let's take a look at the solution. It's actually option D. Now, let me quickly just remind you of the derivation of this. So let's say if I have a velocity profile like this, and let's say from one point, let's say this point, I go down to this point due to some velocity fluctuation v prime, which is negative in magnitude. And due to this, so let's say this was my uh, so I'm going down from here to here, and this is my velocity. So I will experience, mm, yeah, so I will experience a decrease in the uh, u, right? So I will experience a decrease in u prime. So as you can see, this mm, u prime and v prime, they are actually negatively correlated, and they're negatively correlated, and it depends on this length covered by it. So that length is assumed to be proportional to y, and it can be called as equal to kappa y. And this is what we want to model. And on top of that, we know that um, this is a kind of a stress term, uh, which will be modeled as something like this: nu t into dou u dou y. Mhm. Yeah, yes, it is kind of a stress term which looks like this, and it depends on kappa and y. Mm, Oh, yeah, sorry. So what we say is that sorry, these are both independently dependent on y and equal to kappa y. So this will be proportional to kappa square and y square. So these are both, you can say, equal to kappa y in case of isotropic turbulence. And these are proportional to y because as we uh, as we go towards the wall, we should, sorry, as we go near and near to the wall, we should experience, sorry, let me draw this correctly. This is u, this is y, this is the velocity profile, and that's how these things fluctuate. And the idea is that the fluctuations should be zero at the wall, leads us to leads us to the idea that the fluctuation should be proportional to the distance from the wall. So that's how we land on u prime equal to kappa y and v prime also equal to kappa y. These are, of these scales, not exactly equal to, but yeah. So this term, uh, u prime v prime bar should be proportional to kappa square y square, and also the and this will also depend on the slope at this point. So the dou u dou y. So, okay, let me just do this from the start properly. So the idea is that the fluctuations should be proportional to y, and also they should be proportional to the uh, the slope or the gradient of velocity existing there. Because for the same length covered, the increases would be more. So one model or one scale for both of them is that they would be equal to kappa y into dou u dou y. This would be the scale for both of them. Now I have to determine the u prime v prime bar term, which we treat as a turbulent stress. So we multiply the scales of both of these terms, which turns out to be kappa squared, y squared, and the magnitude of dou u dou y squared. And this is dou u bar, that is the mean velocity squared. So this is what mu t is equal to. Nu t is equal to. So nu t should be equal to now the kappa squared, y squared, and we had a square here and one term over here. So they will cancel out and we will get mod of dou u bar dou y. So that is the turbulent eddy viscosity nu t for according to Prandtl's mixing length theory. And I'm sure you can see that this is exactly equal to option D, which should be the correct answer. All right, moving on, we move on to question number 7 now, which is asking us what does the momentum eddy diffusivity nu t and the thermal eddy diffusivity alpha t depend on. Now these are all they appear in turbulent boundary layers. Now, not just boundary layers, turbulent flows in general. So what do they depend on? So is it option A, the fluid properties? Is it option B, the flow field properties? So I should say properties. Or is it option C, that both A and B? Or is it option D, none of the above? So let's take a look at the solution. It's actually option B, the flow field alone. So if you saw earlier, this nu t previously, according to Prandtl's mixing length theory, we could see that it was kappa square, y square, and dou u bar, dou y only. None of the fluid properties ever showed up. It was just you know, the dimension y and u bar, that is the mean velocity gradient, and kappa, which is a constant, not dependent on the fluid properties. So it's entirely the flow field created by turbulence that determines what this momentum eddy diffusivity and thermal eddy diffusivities would be. These are purely kinematic properties. They don't depend on the properties of the fluid itself. Okay, so that's why the correct answer should be option B, the flow field properties. Okay, so moving on, we move on to last question of today's session, which is an interesting one. So there are four lengths given, L1, L2, L3, L4. We have to arrange them in a proper order of their magnitudes. There are four options given below. And what do they mean? So these are all entrance lengths of some sort. So L1 is hydrodynamic entrance length for laminar flow. L2 is thermal entrance length for laminar flow. So I'll just write them in a better way. So L1 is L hydrodynamic. I'll say H, and laminar. I'll write lam. L2 is the same thing, thermal for thermal entrance length. So T for laminar flow. L3 is hydrodynamic entrance length. So LH, comma, for turbulent flow. So that I'll write as turb here. And similarly, L4 is the thermal entrance length for turbulent flow. So this is LT turb. Now, the another condition given is that for Prandtl numbers much less than 1, pick the correct option. So this is another very important piece of information that the Prandtl number is much less than 1. So given this is true, you have to arrange L1, L2, L3, and L4 in the correct order of their magnitudes. So the options given are option A, L1 less than L2 less than L3 less than L4. Option B says that it should be L4 less than L3 less than L2 less than L1. Option C says that it should be L1 less than L3 less than L2 less than L4. And option D says that L4 less than L2 less than L3 less than L1. So you have to apply your, concepts of entrance length and boundary layer growth for laminar and turbulent flows, uh, along with the fact that Prandtl number is much less than 1, and make judgments on which of these should be the smallest, which one of these should be the largest, and intermediately where the other two of them lie. So let's take a look at the solution. It's option D. Let's see how can we get there. So I'll just use these things which I wrote here. So first of all, Prandtl number is much less than 1. So as a result, we know that the thermal diffusivity is much greater than the momentum diffusivity, right? So in both cases, the thermal boundary layers would be bigger than their corresponding hydrodynamic boundary layers. So the first piece of information that comes from here is that the thermal boundary layers for each cases. So LT laminar would be smaller than LH laminar. So for laminar case, the hydrodynamic boundary layer will be bigger than the thermal boundary layer. Or sorry, the other way around. So the thermal boundary layer will be, oh no, sorry. So the diffusivity being high, so diffusivity being high means that the boundary layer will grow quickly. So let's say if I have two cases like this, I have one case in which I see a slow growth like this versus a fast growth like this. So this faster growth would have a smaller entrance length, right? So if the diffusivity is high, the boundary layer growth is high, and as a result, the entrance length is small. So since alpha is high, the thermal boundary layer will grow at a much faster rate than the uh, hydrodynamic boundary layer. And as a result of that, the thermal entrance length will be smaller than the hydrodynamic entrance length. So LT laminar should be less than LH laminar, which corresponds to uh, L2 being less than L1. And also, it means that LT turbulent should also be less than LH turbulent. So in the turbulent case also, the thermal boundary layer will grow much more quickly and the entrance length will be smaller. So this tells us that L4 should be less than L3. So these are the two things that we have as of yet. And on top of that, we know that in turbulent cases, the boundary layers grow more quickly, right? So uh, these two entrance lengths, L3 and L4, which correspond to the turbulent cases, they will be in turn smaller than the laminar cases, which corresponds to L1 and L2. Now, this is what we have, and this is what we have, and this is what we have. So if we stitch together these three things, what I get is that L4 less than L3 and less than L2 less than L1, which is option, sorry. Mm, okay, it could be the other way around as well. Okay, so let's look at this from this angle. So the turbulent boundary layers are smaller than hydrodynamic boundary layers. So, sorry, the third, I'll just write this down. So turbulent boundary layers grow faster. So turbulent entrance lengths are smaller than the laminar entrance lengths. So this means that the two turbulent cases. Um, so if we compare the hydrodynamic ones, so L1 between L1 and L3, uh, L3 will be smaller than L1. And for the thermal case, the turbulent one, that is L4, should be less than L2. And also we know that since Prandtl number is much, much less than 1, nu is much, much less than alpha. And as a result, the thermal boundary layers or the thermal entrance lengths will be less than the hydrodynamic boundary length or entrance length. So the two LTs are these two, L2 and L4, and they should be in turn less than L3 less than L1. So yeah, so 4, 2, 3, 1. This should be the correct order, which is option D. Okay, so that's all for this week. Thank you. So in the next 2 days, we will meet for week 12, and also we will have a revision session on the day after. Okay, so thank you.